Hey guys, so welcome back to your next class of Catalyst concepts. In the previous sessions, we looked at what are series and parallel connections and how do we find out the equivalent resistance of each of them, right? So we'll just look at one quick example of how we can go about it when there are big circuits involved. That we looked at simple circuits so far. So what if we get a circuit like this? How will I find out what is the total resistance here? If I take a look at it, there's a combination of both series and parallel, right? So if you see at this junction, both of these have become like a parallel connection, but they again join in series with this third resistance. Right, so let me just label them as R1, R2, and R3 for easy reference. So how will I find out the total resistance for this circuit? This is where the series and parallel connection rules will come in. Okay, so first I know that R1 and R2 are in parallel, correct? So if they are in parallel, then what I'm going to do, I can use the equivalent resistance to find out how can I replace them. So I can say that 1 by R equals to 1 by R1 plus 1 by R2. Okay. I didn't write R equivalent because it's not the final one. For now, I just wrote it as R. So I can write it as 1 by 4 plus 1 by 12. It's nothing but if you take this LCM, it's 12. So you'll get 3 plus 1, nothing but 4 by 12, 1 by R. So R equals to 12 by 4. So nothing but 3 ohms. Okay. So both of these parallels can be replaced with one resistance of 3 ohm. So what I can do now is I can reframe this diagram like this. Okay. I can just replace these two with one resistance of R equals to 3 ohms, something like that. Okay, I have replaced just this section with its equivalent resistance and put the other one, that is R2, R3 equals to 5 ohms, and then continue the rest of the diagram. Okay, now these two are in simple series connection. Okay, so now I can find R equivalent as nothing but R plus R3, which is nothing but 3 plus 5 is equals to 8 ohms. Okay, so the total equivalent resistance for this original circuit is nothing but 8 ohms. Okay, so that is how we can find out. If you want, you can you make a simplified diagram like this also. It's not really necessary, but the point is to know that the total resistance for this circuit will be of 8 ohms. Okay. Now these two formulae are well and good whenever there is like one simple circuit involved like this. Okay. But sometimes what happens is you'll find a type of circuit that you cannot use these laws directly on. These two formulae you cannot really use directly on them. In that case, you might need to use something else. For example, what if you have a circuit that has multiple batteries? What if you have a circuit that has multiple branches or connections? Then what are you going to do? Right? In that moment, you cannot use these two formulae. For that, we have a different set of laws. Okay. So there's this one scientist whose name is spelled like this. Okay. It's pronounced Kirchhoff. It's a weird way to pronounce it. I know it's called Kirchhoff. It kind of says looks like Kirchhoff, but Okay, it's pronounced Kerhoff. Anyway, so what this person did is he has two laws framed just for these electrical circuits, and both of these can be used for pretty much any type of electrical circuit. Okay, we'll go through one of these today. We'll try to implement it and see how it works, and in the next class we'll look at the other law. Okay, so these two laws are called as, one is called as junction law, the other one is called as loop law. Okay. So let's go through the first one, that is called junction law. Okay. Now, what does this junction law by Kerhoff tell us? It says that total incoming current at a junction is equal to total outgoing current from that junction. Okay. Now, what is a junction? A junction is nothing but a point where multiple conductors or wires are connected. Okay, for example, in this diagram here, this is a junction. Okay, at this point, there is one wire coming like this, and then it's splitting into two different wires or connected to two different wires. Okay, it's a junction that has three connections. Now a junction does not need to have only two or three, it can have many connections. Okay, like for example, say that there is a junction that looks like this: 1, 2, 3, 4, 5. Okay, I have drawn a junction with 5 different conductors. Okay, now we know that each conductor is going to be carrying a certain amount of current with it. Say that this one is carrying current like this. Okay, I will call them as I1, I2, and this one I'll say outward I3, and I'll say this one is I4, and I will call this one as I5. Okay. Now you have 5 different currents coming from conductors at this junction. If I have to go by this law, what it says is total incoming current at the junction is equal to total outgoing current. Okay. So what is the total incoming current? What is the current coming towards the junction? You need to simply look at the arrows and tell this. Okay. I can say that I1 arrow is pointing towards the junction. So I'll say I1 is incoming. Okay. Even I2 is pointing towards the junction. So I2 is also incoming. Okay. I3, however, is going away from the junction. Look at the arrow. Okay, so that is not an incoming current. I4 is again going towards the junction, which is an incoming current. I5 is again going outward, right? So these three, this is the total incoming current. Okay, so I will call this as total incoming current. He says that this will be equal to the total outgoing current. Now, total outgoing current, you will just look at it in the same way, but going in the different direction. So the opposite way, that is nothing but I3, which is going away from the junction, plus I5. Okay, so I3 and I5, if you add, you'll get the same value that you get for I2, I1, I2 and I4 combined. Okay, now since this is again an equation with variables, once you have a few values, you can solve for the unknown value also. Okay, let's take a simple example for this. let's assume that uh, I1 equals to, since this is current, we'll take it in amperes. Okay, let's say 2 amperes. Let's say I2 is 4 amperes. Let's say I3 is 6 amperes. 6 amp. Let's say I4 is 10 amp. Okay, and let's say what is I5. Okay, so I have 4 variables with me and one unknown. Okay, so how do I find it out? Simply using this equation. Okay, now if I substitute these values, let me just solve it, simplify it over here, right? I just write the equation again. I1 plus I2 plus I4 equals to I3 plus I5, right? Simply if you put the values in, I1 is nothing but 2 plus I2 is 4 plus I4 is nothing but 10 equals to I3 is nothing but 6 plus I5, which is nothing but a unknown value. Now 2 plus 4 plus 10 is nothing but 16 equals to 6 plus I5. How to find I5? I'll send 6 to the other side. I5 equals nothing but 16 minus 6. Okay, this 5 is a small 5. Okay, it's in the name. It's not a number as such. It's just the name, I of 5. So I5 is nothing but 10 ampere. Okay, so if I5 is 10, you'll see that I3 plus I5 is nothing but 10 plus 6, 16, and these three are also combined 16. So total incoming, total outgoing will be the same. Okay, it's quite a simple thing, not really a lot of logic to it. You just need to remember to look at the arrows, incoming all together, outgoing all together, equate them, and you'll be done. So that's all for today. If you have any questions, please drop them in the comments below, and I'll see you guys again in the next class. Thank you very much.